from the title, my talk will be split into mainly two parts. Namely, after an introduction into some sort of multiscale methods. Of course, I don't have to be too long here, I think, in this audience. I want to consider two different parts, nonlinear problems and then randomly perturbed problems, and I will, of course, tell you a bit more what I mean by that and what the challenges are and what we've come up. So, yeah, this somehow sometimes is a bit lacking. So let me motivate. Of course, I think in this audience I don't have to motivate a lot that a lot of application problems require us to look at multiscale problems. For instance, we've already heard it in the first talk. If we want to look at modern composite materials or metamaterials that are used in various applications to obtain enhanced properties, we had some very nice examples in the first talk. This often has some fine scale structure that is much smaller than in comparison to the length scale of our general problem. This is typically called a multiscale problem, and we've already heard and seen as well that we will need computational multiscale methods to solve such problems. We've already also seen the list, and I don't want to deny it, of various available computational multiscale methods that are around. In this talk, I want to focus on the localized orthogonal decomposition method. I will briefly introduce this method in a minute. But first of all, I would like to highlight what the challenges for the LOD, but I believe also for many other multiscale problems are when we look at what I mentioned, nonlinear and randomly perturbed problems. So I believe that some of the challenges and maybe some of the ideas I will present today are even more general than looking at one specific multiscale method, which I, of course, will then later do for my analysis and my numerical experiments. So, two parts, two columns here. Nonlinear problems, they are typically used to model problems where you have high stresses, high intensities, high forces, where the linear material models that we typically use and where we end up with linear PDEs are no longer accurate enough, because these linearizations, in some sense, they are some approximation of the reality. And if you go to high intensity in light, for instance, or high forces in elasticity, you often need some sort of nonlinear material response to capture this. Then you end up with a nonlinear PDE, and if I put it very broadly, one challenge that you can have, and we will see it in some sort if you just look into one of your textbooks with your multiscale methods and try to write it down for the nonlinear or for a simple nonlinear problem in a similar fashion, you quickly realize that the typical construction of multiscale basis functions in some sense or another is typically based on linear arguments, and then you run into trouble when you look at nonlinear problems because you can't directly transfer these things. This is kind of the overwhelming challenge in my view there, and I want to address this a little bit here. The other one is maybe a bit not so clear what I mean by that, randomly perturbed problems. I will give you one model later on as well. I in general see this as one way to model things like fabrication mistakes or defects, that you say that you have some sort of random or uncertainty model where these defects can appear. And this means that you then have one multiscale problem, but that the material can have different realizations depending on what defect you have. And if you want to do some sort of assessment in the area of uncertainty quantification, you have to simulate the same multiscale model for different multiscale coefficients that are somehow similar but not the same. And you have the challenge that we've already seen this in the first talk. This is also very a common challenge for multiscale methods, that the multiscale basis functions that we construct typically rely on the multiscale problem you want to solve. So if you have a slightly different multiscale problem, you have to recalculate your multiscale basis, at least in theory. But of course, if there's only some sort of small, whatever small means, change, you would hope to reuse parts, and the question is how you can reuse this, when you can reuse this, and how to make best use of it. So these are the two general challenges I want to address in my talk. But before coming to each part separately, I want to briefly put us all on the same page concerning the multiscale method I will then have a look at, namely the localized orthogonal decomposition. Some brief ideas how this works. So I will illustrate these ideas at the simplest multiscale problem possible, the elliptic multiscale problem that you all know, where we try to find a solution U in H10 or some fine scale reference space. So this is kind of my true or reference solution to the following problem, where F is an L2 right hand side and A is now a multiscale function in L infinity. It's not sign changing here in contrast to the previous talk. It's spectrally bounded from above and below, so uniformly elliptic and bounded as usual. And the name of orthogonal decomposition goes down to the fact that we try to decompose ideally our solution space V, so imagine H10 here, into two spaces and orthogonally with respect to the energy product induced by this bilinear form B here. And how do we construct the two spaces? We first fix the so-called fine scale space W. You've seen such an idea as well already, namely as the kernel of some interpolation operator. It could be the L2 projection, but can be also some other stable interpolation operator, IH mapping from H10 into a coarse finite element space on the coarse scale H. So why do I call the space W fine scale space? Because these are all the functions that are not visible on my self-set coarse scale capital H. They cannot be represented by the coarse finite element functions. They are kind of not visible on my scale capital H. And then I construct the space in which I want to approximate things in the end as the orthogonal complement of this fine scale space. And it turns out that this new space VHMS for multiscale in fact has the same dimension as the a coarse finite element space. It can be namely written as a kind of, you take your finite element space and you subtract so-called corrections of your finite element functions from that. So you have the same dimension. This results in what we've already also heard, that you have small dimensional systems in the end. But the problem is, we also heard it that in order to compute these correction operators Q in this ideal setting, they would be global problems, so on your whole computational domain, which is of course practically not feasible and not desirable. So that's why a second step comes in, namely the localization step, where we give up a little bit of this orthogonality in order to come up with localization, but still, of course, use this idea, namely the idea from the very last line on how to construct a new space of the same small dimension, but with better approximation properties. And the idea is to replace this kind of ideal correction operator Q with something that is more local and still has good properties. So the localization procedure is as follows, and of course I should say here, this, what I present, is the kind of by now classical version of the localized orthogonal decomposition, going back to various people, most of them, a lot of them in the audience. And the idea here with the localization is again that we introduce patches, as you have seen in the previous talk. Here I don't name them Km but Um, and the T is the element from my coarse triangulation, and then I put M layers of elements around it, similar to what you've seen before. That's the first concept I introduced, and then I introduced kind of localized fine scale spaces, just by saying all functions in the fine scale space that are zero outside such a patch. And this is required to define so-called element-wise correction operators, QMT, which I then later on just sum up to form my QM, my localized correction operator, which replaces the Q from the previous slide. And so this QMT, what I need to compute in reality, has three distinct properties, namely that it's still a fine scale operation, it still maps into this fine scale space W. It's now somewhat local in the sense that its support is just contained in this patch and no longer on the whole computational domain. And we kind of retain this orthogonality property by requiring that it's a somewhat almost a projection with respect to the energy scalar product. Namely, we solve the following multiscale problem on the patch using our coefficient A given by the problem here. And then you can, using this, you can make up your Galerkin version of the LOD method, which you can either understand as a Galerkin procedure on the new space, taking finite element functions minus their defined localized corrections here, and then doing the Galerkin method with respect to this space here. That's how I've written it here. Or you can also interpret it as that you search for something in your coarse finite element space and modify your bilinear form here by inserting this identity minus QM everywhere. And that's the two ways how you can interpret things. And it turns out, I did not put it here, that in fact this UHM is a good approximation to my original reference solution U. And let me briefly remind you, having now at least run through the construction of the LOD, that I want to solve either nonlinear problems or randomly perturbed problems. So for the nonlinear problems, we will see this in a couple of next slides, that if I try to rewrite this construction, but B is a nonlinear form, that I suddenly run into problems of having nonlinear problems and even more nonlinear operators and nonlinear somewhat spaces. And that's something I need to overcome. For the randomly perturbed problems, it's maybe slightly more subtle, namely that this Q and thereby of course also my multiscale space, as you can see from here, depends on my coefficient A. So if I have these random defects, so if I have the same coefficient but with small defects several times, this coefficient is slightly different each time, and I have to think about how this changes my multiscale basis in the end. So that's what I want to tell you in the rest of the presentation. Let's start with the nonlinear problems, and I want to briefly give you an overview of what we've done in the LOD context here, and then I will focus on one particular thing. So basically, one could say that there have been two different approaches that we've been considering, that I summarized as first discretize, then iterate, and as first iterate, then discretize. Let me explain it. I will concentrate later on the left part, where we kind of first choose one multiscale space, similar to how we would think about it in the linear world, and then use this in a Galerkin ansatz to solve the nonlinear problem. And here the challenge is how to choose this one specific multiscale space, because we will realize that somehow we have to go around these linear arguments, and we will do this in some sort of linear fashion. And I will tell you more details about this in the upcoming minutes on the example of nonlinear strongly monotone problems, where you can read up things here, and also in the context of non-monotone problems which is a work in progress together with Maya Kreis, who is also in the audience. The other approach that I just want to briefly mention, that it's also there, is that you first look at your nonlinear problem and think about okay, I have to, in general, anyways, no matter how I discretize things, I have to solve a nonlinear system in the end, and there are iteration schemes to do this. So you first choose your iteration scheme. You can often do this on the continuous level for the PDE. You write down your iteration scheme, and then in each iteration step, you typically have to solve just a linear problem. And then you're back into business because you're typically in a typical linear PDE setting for which you know how to construct your multiscale space. So that's why I call it first iterate and then discretize, or first choose your iteration scheme and then think about the discretization. And this is also very attractive. It has then, of course, the challenge similar to the randomly perturbed problems that you have to construct a multiscale space in each iteration step, because in each iteration step, typically your coefficient or the linear problem you need to solve changes because it's updated based on your iteration. Of course, there's some structure in there as well that one can try to exploit, and that's kind of the business of this approach. But for today, admit me to consider this part where we try to come up with one space and then try to do a Galerkin scheme for our nonlinear problem, and I will not speak about how to solve the nonlinear problem then in the end, the global one, because there I assume to use some standard method like Newton method or whatever. So what type of problem do I want to have a look at? Rather simple one, so kind of nonlinear diffusion type thing. I wrote it the following way, so you have this gradient u, gradient v, and you have my coefficient a from previously, but now it does not only depend on the spatial location x, but may also depend on u and the gradient of u. So this is what makes up the nonlinearity. So we still have a right-hand side f in L2, and for this a, we assume it to be multiscale, again in the previous sense, so it's only L infinity with respect to x. But it's assumed in the nonlinearities they are assumed to be rather smooth, so let's say C1 with respect to u and gradient. And then you can have different cases, not only those two, but these are the two that we had a look at so far. So the first one is where you just depend nonlinearly on the gradient of u. So no dependence on u in here. And then you have a couple of assumptions that kind of imitate the things from the linear case, like uniform spectral bounds from above and below. So here it reads as a Lipschitz continuity with respect to the nonlinearity, and the second point is called the strong monotonicity thing that gives the name to this case, and the third one is that if you are linear, then you're so that you kind of retain to the linear case. The non-monotone case does not kind of satisfy this version. So there you have a non-linearity. So you are linear with respect to the gradient, but you're non-linear with respect to the function itself. And you have like similar assumptions. You have some sort of Lipschitz continuity with respect to the non-linearity. And then kind of this one here plays the role of a kind of diffusion coefficient, so you want to have some sort of uniform boundedness and ellipticity here as well, and uniform with respect to u. That's kind of the technical assumptions that are quite standard in the literature here. But we took kind of the most simple examples to explore what our multiscale methods mean for that. So let's try to write down the LOD that I presented previously, so without localization, for this nonlinear problem. And let me recap. So we ended up with having a Galerkin procedure where we had something like a multiscale space which was formed like identity minus some correction operator applied to the finite element space. And then we solved the global problem using this multiscale space. This is what is written here. And then we had this correction operator, be it in the ideal or in the localized version, that was a kind of projection from the finite element space, let's say, to this kernel space. That's the important thing. And what it needs, this projection property, you summarize in the following way, or this orthogonality, that this correction operator minus the function itself tested with functions from the kernel space should be 0. This is, in the linear case, this is a complete equivalent rewriting of the so-called ideal method. And now I just write my nonlinear B here everywhere. I can, of course, write down whatever I like, and I have a closer look at it, and I realize, okay, this means, because things are nonlinear in the first argument here, this means that this operator Q gets a nonlinear operator, and thereby also this, I don't know, space, this object, the set where this solution should come from, becomes something nonlinear as well, and I use this as test and ansatz, or I would like to use it as test and ansatz space in my method. I don't want to say that this is not possible, but it raises a lot of questions whether it's possible, how it is possible, whether everything is well posed. And in order to circumvent these things, the first thing we did was a very simple, maybe too naive idea, is to say, okay, if I find a good space here, I can maybe live with solving the coarse problem, the coarse nonlinear problem. It's something I would need to do even with the coarse finite element discretization anyway. So let's think mainly about the construction of this space and the construction of this correction operator. Can I make this linear in some sense to avoid all these difficulties of the nonlinearity? And that's the kind of idea that comes here in blue now. So the top part hasn't changed. I still solve a nonlinear problem to obtain my solution in the end, but I construct my space now in a different way so that it's in the end a linear space as before. And namely, I replace the B here with a bilinear form A that is now really bilinear. Namely, for simplicity, let's first put it, it should have the typical diffusion type property with some uniformly elliptic coefficient, it may depend on x, fractal A. So this means that in order to calculate Q, I have to solve linearized elliptic so-called corrector problems, and then I'm back in my Galerkin construction for the nonlinear problem. Okay, this is on the one hand nice, because everything, the construction is now linearized, and I'm quite sure that this blue part is well posed if I choose bounded and linear and uniformly elliptic A. But remember, we've also seen it in Eric Schung's talk, a lot of the error analysis for the whole method hinges upon this orthogonality thing, or that we kind of use knowledge of our problem in the construction of the multiscale space. So somehow I have to be at least careful at how to choose this linear, this fractal A, or this bilinear form A here. I cannot just do anything here. It has to still do something with my linear problem in order to be sensible. And that's what we thought about next. So this is just the reminder. We want to solve this linearized elliptic problem. And how can we choose this fractal A now? There are several ideas inspired from typical iterative methods, and they look a bit different whether I'm in this, I depend non-linearly on the gradient, or I depend non-linearly on the function itself. So let me go through it. So first of all, the choice always hinges upon, and we'll speak about this a bit more later, that I choose or fix some what I call linearization point, some specific function U star, around which I kind of linearize my nonlinearity in order to generate the fractal A. And I can do this in different ways. This Kachanov type is sometimes also called frozen nonlinearity thing. So you see it here, if you have this type of structure here, you can just say, okay, I want to have a diffusion type problem, so I just replace the nonlinearity by fixing the function at which I evaluate the alpha tilde here to be this fixed function here, and then things are linear with respect to gradient u. And for the non-monotonic case, it's even easier because you had already this natural structure of having a diffusion coefficient times gradient of u, so you just freeze, that's what it's called, freeze the nonlinearity at your previously chosen linearization point. The Newton type thing is like from some sort of first order linearization, or doing one step of, or inspired by doing one step of Newton type thing, or Frichet derivative. And in the monotone case, you just take the Jacobian of your nonlinearity A, oh, it should be an alpha here, I think. The nonlinearity of your, the Jacobian of your nonlinearity with respect to the nonlinearity and evaluate it at that point. For the non-monotone case, I don't want to go through the formula in detail. What I want to highlight is that for the non-monotone case, this is a bit different, especially it does not directly give me such a diffusion type problem, but more a convection diffusion type problem. That's just to remember for some side remarks later. But you can, first of all, you could write it similarly. Okay, then except from the choice of the linearization point, you start from the previous slide with these things that I've told you. We have fixed all the things for the that we need for the method. I did not speak about the localization procedure because since I've linearized my correction problems and they are of a diffusion type problem, I can do the standard steps from LOD multiscale methods with this localization again, so I don't want to bother you with this again. But I want to present some elements of error analysis also in a sketchy way to just convey ideas. So the idea is that we can estimate the error between our reference or exact solution U and this LOD solution, which I call UHM here now. So H for the coarse mesh size, M for the patch size. In the H1 semi-norm, let's say, by the typical multiscale method discretization errors, linear conversions with respect to the coarse mesh size and some exponential decay in the patch size, as we've seen before, times the L2 norm of the right-hand side, plus some additional error, which I call the linearization error, and that typically, first of all, depends on U minus U star. So U star was the linearization point and U is the exact solution. And in the non-monotone case, we have some sort of a posteriori type thing in there, also on the difference between U star and the discrete solution. And I don't spell out how this looks like exactly, because depending on which linearization model you choose, you can estimate this additional term further. The message should be here that this is kind of a linearization error, and we have to make sure that, or we hope to make sure that it's small enough so that we see the typical convergence behavior by choosing U star appropriately. So summary linear conversions up to a linearization error. And one side remark, you've seen this bottom right thing in my table before. This Newton type linearization for the non-monotone case was of a convection diffusion type. There you have to work a little bit more to make sure that your kind of local problems to construct the multiscale basis, that they are still well posed. I don't want to go into the details here, but it's possible. And I want to briefly mention, because U star should be ideally close to, for instance, the exact solution, let's think about how we could choose U star. Because we can't choose it as the exact solution because we don't know it, that's obvious. Okay, the first thing that we've come up, if you don't know anything, you just do some arbitrary guess, because you would need to do some arbitrary guess in your starting value for the iteration anyway. The other thing that one might think of is to take to solve once a finite element system on the coarse mesh. This does not resolve the multiscale things properly, but maybe already gives us some information about how a solution might look like a little bit. It might be a better guess. Or you could also think of the doing the procedure that I've presented 1, 2, or several times. Like you start with a guess, you solve the problem, and then this solution you take as your new linearization point and restart the thing again. And you're a bit in an additional iterative loop as well, and the hope is that things get better from time to time. In the numerical examples, or in the brief numerical example I want to present, we went for the very simple thing of just taking some arbitrary guess, which in this case was even 0. So the most simplistic manner. And the basic message here was that for some simple models that we tested, in fact, this already gave the desired convergence rate that we predicted from the theory. So this is the linear convergence, and you see that we can almost match this with this LOD type thing in the monotone case as well as in the non-monotone case. Of course, if you have a more complicated non-linearity, generally I expect that things will not be that nice, but the first things were already quite promising. Considering time, I would like to shift gears now and move from the non-linearity to the randomly perturbed problems. And first of all, I would like to tell you how I will understand randomly perturbed for the moment. Namely, I want to have a look at the diffusion problem, again a very simplistic problem to focus on the ideas, where the coefficient A is a realization of the following form. So we have some kind of deterministic coefficient and some other deterministic coefficient that is kind of switched on, switched off in some sort of random fashion. I will give more details about the assumptions on A and B and BP in a moment. What you should have in mind for the rest of this talk are these two pictures. They are kind of examples of what we have in mind, and also are examples of what we've tested our methods with typically. The left-hand side, we call it, in our own language, we call it random checkerboard, because it's basically that the A here, so this unperturbed thing, is a constant coefficient, so a white background, and then at predefined locations, I throw an unfair coin, and if this coin shows head, I insert a black dot. This makes up this specky thing, and the black dot is kind of the defect. It's kind of, it should be all white, but there are some jets of ink or whatever there. That shouldn't be there. So there should be not too many black dots. I think this is for some defect probability of 10%. The other one is maybe a bit more what one would imagine a defect in a fabrication to be. So you have some sort of periodic background thing, so white background and periodically inserted black dots, here it's squares. And then the defect means that I throw again an unfair coin and certain of these black dots disappear. This is kind of, my printer did not, my maybe 3D printer did not print the material the way it should. Having this in mind, what is my goal? I want to, hopefully efficiently, compute the solution U to my diffusion problem with these realizations for many different realizations. So I'm not directly going into the realm of stochastic homogenization of trying to come up with some homogenized tensor here, but directly trying to assess the solution, and then afterwards kind of I want to deploy the means on how to quickly compute many solutions, and then you can do, I don't know, Monte Carlo, quasi-Monte Carlo statistics for expectation or whatever statistics afterwards if you like, and I don't mind about it. So this part I will not talk And the problems I want to have a look, as I said, is diffusion problem, either as a kind of source problem, where you can find the details here, or as an eigenvalue problem, with which is ongoing work together with Deline Colombaga, who is also here this week. So let me briefly present the model in a bit more detail. So you've seen this elliptic part here on the left-hand side, and then either a source term or the typical eigenvalue term here. For simplicity, my domain will be a d-dimensional hypercube, and I set periodic boundary conditions. And now again, let me remind you, the A should be kind of this form. This A epsilon and B epsilon should be epsilon periodic things, so you can write them as a one periodic blueprint evaluated at x over epsilon. So everything should be nicely periodic to exploit this structure here. And now I come to this, how are these random defects? Remember what I told you, that I want to, at predefined locations, I want to throw an unfair coin to decide, switch on or off a defect, and this is modeled in a mathematical manner. It looks a bit complicated. In this way, you have a bunch of indicator functions that are kind of at predefined locations Q, that are scaled with epsilon and shifted all around the place. And then at each location, you throw an unfair coin. So this B hat here is Bernoulli distributed with parameter P, and you have many of them that are IID. They are all independent from each other. And then if BP is 1, you have A epsilon plus B epsilon as your value there. And if not, you just have the kind of background A epsilon there. That's the model that we also took from the literature. So, and for this, I want to present a so-called offline-online strategy, where the idea is that we have an offline phase. I think this that is done once, and that may take some time and some memory or whatever. And then for each sample in the online phase, I'm rather fast. So what is the offline phase about? The offline phase, I do two things. So first of all, I just fix one single element of my coarse mesh. Because of periodicity, it's sufficient to do this for one element and its surrounding patch. And there I select, I will talk about this in a second, I select so-called reference coefficients AI, for which I pre-compute and store the contribution to my stiffness matrix in the LOD framework. This is written here. So when these are the hat functions, you have to calculate this nasty looking thing. It's a small rectangular matrix. You have to compute the correctors for these reference coefficients for these bases, for these hat functions, and you have to calculate such integrals. So this gives a small rectangular matrix. And how do I build these reference coefficients? This is also done deterministically, and it's very important to do it this way. And I want to illustrate, there's a formula on how to do it, but I want to illustrate this at my two examples. The A0 is always the kind of unperturbed background. So either the completely white type thing for the random checkerboard, or the perfectly, having all these black dots, the perfectly periodic thing for the random erasure for the right part. And then one by one at all possible locations, but only within this small patch, so this is not the whole domain. One by one I insert one single possible defect. So A1 is here in the random checkerboard having one dot left, and then the next location here, next location, etc., until you have all over the place. These are quite a number of things, I admit, but they are less than if I consider the whole computational domain, and of course even less than if I consider all possible combinations. Random erasure is similar, you erase one by one of these black dots. So having pre-computed all these things, in the online phase, I then first loop over all my coarse elements of the triangulation. And for one element of triangulation T and its surrounding patch, I can write the realization, the coefficient A that I'm given, as a convex combination of my reference coefficients. So I can write it as a sum over some coefficients mu I, ai, where these coefficients sum up to 1. This looks like I would need to solve a linear system, but in fact I do not need to. In fact, I just need to take the realization I'm given and have to basically look at where I have defects. And then I set the corresponding mu's to 1 and all the others to 0 and sum up. So that's something I can hardcode in, that I can kind of already solve on a sheet of paper and hardcode into my code. There's no matrix inversion or whatever involved here. And then having obtained for this specific element these coefficients mu I calculate a contribution to a stiffness matrix simply by taking the same combination from the pre-computed stiffness matrix contributions. I simply build the linear combination with these mu I coefficients, and then this I do for every element T, and then of course I do the usual thing, I loop over all the elements and sum up all the local contributions. Let me emphasize that this is in fact a good approximation of my true multiscale stiffness matrix. This is kind of somewhat a surprise at least, because there's no linear structure in how these matrices are constructed. You would have this linear decomposition if you would do a finite element method, because you had a linear decomposition of your coefficient. But since our basis functions depend on the coefficient again, all this thing is a linear business, and we have to make sure that this simple trick in fact works. That this B tilde, that's why it has a tilde, because it's not the right stiffness matrix, that this is in fact a good approximation to the real multiscale stiffness matrix I would need to compute for my given realization. And this is part of the error analysis that we've done. I can write down a rather explicit result for the one-dimensional case. We also have a result for the higher dimensional case. I will comment on that in a moment. In the one-dimensional case, I can kind of bound the consistency error, so the error between the stiffness matrix I would need to use in theory and the one that I in fact use in practice with my offline-online strategy by some quantities that depend on the contrast, and then basically this theta defect, which is somehow the fraction of defects, or the maximal fraction of defects you have in your realization. So it's not statistically correct, but imagine this to be the defect probability P. Then I think things become a bit more clear. And the defect probability should be small, and the error analysis tells you that it's somewhat quadratic in P with a small linear term. And this explains why, what you will see in a moment in the numerical examples, why in fact this approach works for small defect probabilities quite well. And higher dimensions, we still have a result, but it's not as explicit as it's in this box here. That's why it's not on the slide. In fact, we have an error bound that we can compute in a kind of, together with our offline-online strategy, so in a kind of a posteriori manner, using an error indicator type thing. So we have a computable upper bound that we can use to evaluate. And so this is the error estimate for the consistency error. So how do I get an error bound for my solution with the offline-online strategy? So for the source problem, you can simply apply the Strang lemma and get kind of discretization error plus this consistency error. And for the eigenvalue problem, you have to do some sort of perturbation arguments, some sort of I don't think it's called Strang lemma for eigenvalue problems, but something of that sort. And also to make things easier as a side note for the eigenvalue problem, there's the question you have the mass matrix on the right hand side still, which in theory you should maybe use the also a multiscale version of it using multiscale basis function, but with this offline-online strategy this looked a bit complicated, so we simply used the finite element mass matrix on the right hand side because it's anyway an L2 term, so our experiments show that this has no bigger effect, at least not dominant one. And then, for instance, for this random checkerboard, but also for the other case, I want to concentrate on the random checkerboard here. We have numerically evaluated it, and for the source problem 2D thing, let me focus on the blue curve, which is the relative L2 error. Of course, you see an increase with P, and yeah, we can now negotiate, but I think for it's still for up to reasonable defect probabilities you have reasonable relative errors because yeah, typically I would say that I don't want to have a manufacturing defect of more than, let's say, 10% or something. And I still, or up to, I don't know, what is it, 7% or so, I'm below 1% relative L2 error. But this depends, of course, on the application. And if you, of course, you can do some sort of upscaling to also get good H1 approximations. There, the errors are typically larger, but still reasonable. And for the eigenvalue problem, we have something similar. So again, increase with P, so there we looked at the error in the eigenvalues. And what I would like to draw your attention to here is at comparing in the same color the dashed and the solid lines, because there's another twist that we came up with recently. So the dashed lines are kind of corresponding to what I presented before, and the solid lines, you see, they have lower errors here. They correspond to, which is possible in this random checkerboard thing, to using not to constructing these coefficients mu I in a slightly different manner. So they still give this sum for the realization, but the sum of the mu I is no longer 1, but some parameter s that is 1 plus some perturbation. And this comes from some new heuristics that we did, how to choose this s, and in fact we numerically evaluated that it seems to improve things, and it's rather easy to implement. It does not influence the computational complexity that much. And that, with that, I would like to already conclude. So I've talked about a localized and linearized construction of multiscale spaces for nonlinear, mainly a quasi-linear problem. For the randomly perturbed problems, I've spoken about an offline-online strategy. And if you want to really boil it down, my numerical analysis was typically, I have the typical LOD error bounds plus some extra error terms that I carefully controlled with perturbation type arguments that come up for the linearization error or for the consistency error in these in the randomly perturbed case. Before thanking you for your attention, let me give you some short advertisement. I think you're the right audience there, that at this nice hint place there will be a so-called junior trimester program in 2026. Beginning of 2026, so junior trimester program. You possibly know the trimester program we've had here. Junior trimester program is, as the name suggests, for junior researchers that can apply and that are grouped into topical groups, and that then kind of run the program on their own, more or less. So Jürgen, my colleague, and my name are there to be kind of mentors and to select the people and to make advertisement. And I think, so maybe you can, if you have questions, you can contact me during the week. Keep this in mind to pass it on to your group members or any junior researchers you happen to know. And I think you will receive emails by me with advertisement again and again, but already here. And then I'm done, and thank you for your attention.